to the Eastern Iowa Observatory and Learning Center from Cedar Amateur Astronomers. My name is John Leeson. I'm one of the volunteers. Cedar Amateur Astronomers operates the observatory as an all-volunteer basis. We don't have any paid members of the club. And Lynn County maintains facilities. They mow the lawns and plow parking lots, and we operate the telescopes and arrange for the programs and give the programs. So it's a kind of a partnership between us and Lynn County. The partnership is actually a deal between Lynn County and us. They let us use the park for our observatory and have our observatory and telescopes here and on their park, and in return we've agreed to give 12 public programs every year and for free, so 12 free public programs every year. So you'll find on the desk up front, you'll find a little card that looks like this. It has the dates and times for all of our 2013 programs. Tonight is August 24th. We have 3 more, September 7th, October 5th, and November 2nd. So the bottom 3 on the card are still to come. So you're welcome to pick up one of these cards when you're walking through the lobby. Likewise, there's a brochure on the Cedar Amateur Astronomers, so you can get a little more information about Cedar Amateur Astronomers and a little more information about the observatory. You can pick one of those up. If you hear us talk, we use some websites quite commonly. Of course, there's our website, cedar-astronomers.org. Another thing that we have is you'll have up in front, there's a sky map, looks like this. It's got things to look for on the back and some locations of things in the sky on the front, and that's at skymaps.com. So skymaps.com is on this. So pick one of these up too, and it's got some interesting websites that will help you find some things. We also have some things up there that you can buy that you can go and find in bookstores and that, but for convenience, we have a few things that we sell at pretty low cost. Some calendars with pretty pictures and perpetual sky maps. In case you hadn't spotted them, the restrooms are through the lobby, on the far wall of the lobby. So as you're walking out, you walk straight ahead through the lobby to the restrooms. Of course, CAA does have some expenses. We're doing some painting on the observatory and some siding, and we always have things like new projector light bulbs and stuff that we got to buy. So since we're an all-volunteer organization, if you do decide to leave a donation in the donation jar, it's appreciated, and it all goes back into the facility. So you know that it's not going to any place except it's not going for a party. We don't have parties funded by donations. So all of the donations end up going back into the facility. So you can feel good about that. We are a tax-free organization, tax-exempt organization. So donation would be tax deductible. If you choose to give a large one, let us know. We'll get you a receipt. Large screen display over there is NASA ViewSpace. It's a subscription service that we get out of the Space Telescope Science Institute in Baltimore. I'm going to turn it off during the presentation because it's noisy and the sound is irritating and it'll be disruptive. But after we're done, we'll turn it back on. Anytime you want to come in and sit down and cool off for a little bit, you're welcome to come in watch it. We've had the person watch it for 5 hours without seeing the same significant program repeating over and over. So it actually does better than this slideshow that you're seeing up front here that keeps repeating. So the slideshow that is repeating up here, we also have running in the lobby, and so we'll leave that running, and so afterwards, if you missed out on some of this, you can catch it up there. Gives more information about the observatory, the rules, and so on. You'll see there's a table over there by the pass-through into the kitchen. Has a bunch of magazines on it. You're welcome to pick up on an issue or two. Those are extras of magazines. We have a library that we have every astronomy magazine published, I think, along with several hundred books. It's our club library. And we get donations of magazines all the time, and we use them to fill in any that we're missing, and then the extras we have available. So pick up an issue or two, browse through it, take it with you. If you decide you like it, of course, then you can subscribe. So it's a kind of try it before you buy it. I think enough about the observatory. Tonight we have with us Professor Cornelia Line from the University of Iowa. Professor Line received her PhD in astronomy from the University of California at Los Angeles in the year 2000. She grew up in the Midwest and attended Vassar. Got a BA in astronomy and physics in '95 in New York. She started graduate work at the University of California at Los Angeles in the fall of '95 and moved to the headquarters of the Very Large Array Telescope in Socorro, New Mexico in '98 to finish her dissertation research. After receiving her PhD, she had a postdoctoral fellowship at the University of Massachusetts, Amherst from 2000 to 2002, joined the faculty at the University of Iowa in 2002. When not working, Cornelia says she enjoys traveling, reading, running, and adventures with my family, my husband, Mike, and 3 children, Caleb, Amelia, and Will. Go through?
Still true.
So tonight's program is titled Looking Ahead. It's for radio astronomy, new instruments, and exciting science. I think you may have read the full details of that on the web, but I'll turn it over to Professor Lang, and she can fill you in on the rest of it.
Well, thanks so much, John. It's a real treat to be here. I think we have a real synergy between the club here and the university. We really enjoy every semester bringing students out because it's gotten quite light downtown in Iowa City, and so John and Scott and the gang put on a fantastic program when we bring our busloads of students out here. So we really appreciate it, and it's really fun to be able to come back and tell you a little bit about things that are near and dear to our hearts. In particular, tonight, I want to tell you a little bit about the field that I mainly research in, which is radio astronomy. And the reason I chose this is because I think a lot of times we focus on optical astronomy, which is fantastic, and we all love looking through telescopes and putting cameras and CCDs behind optical telescopes and making these beautiful true color images that really capture probably one of the main ways we observe and learn about the universe. However, as you all hopefully know, electromagnetic radiation, or light, comes in lots of different forms. And so the optical part that we usually associate with astronomy is just one very small part of the spectrum. So tonight I want to take you on a little bit of a tour about radio astronomy, which is the part of the spectrum that I mainly do my research in. I think radio astronomy right now is really undergoing a renaissance around the world, and so I want to educate you a little bit about radio astronomy and then tell you about some of the exciting new projects that are just happening right now and then are on the horizon. But I thought I would actually start by telling you two things that are going on at the University of Iowa, partly because I know the club members and others are kind of interested in what we do downtown. So a thing that happened just 2 or 3 days ago is we have a major renovation going on the roof, and this can actually affect everyone locally because we are renovating one of the domes on the top of Van Allen, and we are installing a brand new optical telescope that's going to be bigger than anything we've had on the roof before, and even given the light pollution downtown, should allow us to do some really exciting public observing and also some research projects for undergraduates and graduate students at the university. So the story is that we have two domes on top of the roof that were built in 50 years or so ago, and the larger of the two domes had fallen into pretty bad shape. There were holes in the metal which allowed rain to get through, and the actual motor, the workings that opened this slit, which you obviously need to observe, had failed, and the parts to replace it was going to be quite complicated. And so my colleague Bob Mutel got a grant from the Carver Foundation, and this is pretty smart actually. He kept the cylinder part of the dome, which holds the brand new mount that we bought about 10 years ago, prepared to put a telescope in before we realized this upper dome had so many problems. So this is a beautiful fiberglass dome called an Astro Haven, and it weighs about 300 pounds, not that heavy. And so we had to hire a crane to first take off the old dome and then lift up this beautiful clamshell that can sit right on top of the old existing cylinder that has our beautiful mount inside. And of course, the telescope isn't in there yet. In fact, that's on order. It's coming in October. So we had the crane come. This was Wednesday, and they managed to lift the Astro Haven in its open state right on top of the lower part of the dome. There was some touch and go stuff with the metal. We had a metal kind of a big ring built, and there were some really complicated things with the size of the holes for the bolts that were going to bolt these two parts together. But it all worked out. Scott was there. It was kind of an exciting morning. And it was set into place. This is a sort of an after picture later in the day when the clamshell is up. It's absolutely beautiful. And this sort of shows the situation. We have a couple of radio telescopes that we use for our radio astronomy courses. This dome at the moment is not being used. It's got some other problems. But we're very excited to bring this dome back up to speed. And here's a picture from the Planewave Company website of the telescope that we have ordered. It's a 17-inch optical telescope. We're also going to have a solar telescope, this beautiful solar telescope that's going to sit on top of it. And then I think there's also another smaller telescope, finder telescope. So anyway, this should all be up and running by the end of the semester, and so we're really excited about it. And we hope you'll all stop by when we have public programs downtown. The other thing I thought I would just mention, just because it's just completely consuming me right now, is that we have begun to offer a new course at the University of Iowa with the topic of origins of life in the universe. And I mention this just because it is a topic that's near and dear to astronomers, especially when we're searching for life in the universe. And this is the first time a course has been taught at the University of Iowa over a year by faculty from different departments, all who have the same instructor. So we have a biologist, a chemist, a geologist, an astronomer, and an anthropologist. And we're going to spend a year exploring how life came, how the Earth came into existence, how the universe, what the parts of the universe are, and we're going to take it all the way through the origin of hominids, get to intelligent beings, and then turn back and search for life in the universe. So we're really excited about this course, and so you may hear some things about this. It's a really neat idea that we can bring people together who all have an interest in astronomy and astrobiology. All right, so I already summarized what we're going to talk about tonight. So I want to talk a little bit about radio astronomy as a field, and then I want to show you some highlights and sort of a smattering of It results in radio astronomy that you may or may not be aware of. And then I want to talk about these big new radio telescope projects that are just on the horizon. And some of these are very large, and one of the neatest aspects of them is that these are truly international projects. And as we see toward the end of the talk, the scope of these projects is so large that, first of all, no one country could ever afford to do it on their own. And second of all, you need the expertise and the locations of people from all across the planet. And so these are really some neat things happening. And this isn't just unique to radio astronomy, but there's some exciting developments in our field. Okay, so I'll just remind you of the full electromagnetic spectrum of electromagnetic radiation or light. And so we're most familiar with this very narrow range here, which is the optical part of the spectrum. So we've obviously got the long optical wavelengths are red and the short optical wavelengths are violet. Just shortward of violet light, we have ultraviolet radiation, which we've had a lot of this summer. And we also have X-rays, which are a form of light that you experience sometimes in medical work. And then gamma rays are the shortest type of electromagnetic radiation. And you can see when we talk about short, we're talking about the distance between crests of the wave. You can also refer to this as frequency. So these are very high frequency waves, and down here you have much lower or longer frequency waves of light. Okay? And when you go longward of optical light, you get into the infrared, and then the microwave regime, which are kind of just short radio waves, and then you get into the radio waves. And this is the regime we are going to focus on tonight. And you can see the radio wavelengths span many orders of magnitude. The shortest radio wavelengths even can be fractions of a millimeter, sub-millimeter light. And the longest radio waves can be many tens or even 100 kilometers in their wavelength. Okay, and there's some limitations. There are some limitations with observing this huge range of wavelengths, and you can imagine you wouldn't use the same technique to collect, focus, and detect waves that are very short, less than a millimeter, compared to the techniques you might use for very, very long wavelengths. Okay. The neat thing about radio waves is that we can actually observe them. For the most part, we can observe them from the ground. Okay, so that makes our job a little easier. I think if any of you came to former presentations here, you would probably have heard of some of the space-based observatories like Hubble Space Telescope and Chandra Space Telescope. With much of the electromagnetic spectrum, we're forced to put telescopes or satellites above the Earth's atmosphere, because the Earth's atmosphere blocks out a lot of the spectrum, which is a good thing for us because these very high frequency forms of light, gamma rays, X-ray, and ultraviolet, are very dangerous to the point of being lethal to cellular structures on Earth. And so it's a good thing that we can observe these from the ground, and we can put satellites just in our orbit, but above the atmosphere where these types of radiation are absorbed. Visible light can make it completely through the atmosphere, and you can see infrared is very variable. So this shows that all of the radiation is blocked, and the dips in this plot show that it can get through to the ground. Okay, so you can see that visible light can make it all the way to the ground. The infrared is a really mixed bag, and this depends on how high you are up on in altitude on the Earth. The higher you are up, the more chance you have to observe some of these infrared wavelengths. All right, but that's the short infrared wavelength. Most of the mid-infrared wavelengths cannot be observed from the ground, and they have to be observed from space. And then you dip into this beautiful deep window that's the radio window. Now, there are some limitations. At the very longest wavelengths, the radio waves are blocked by a part of our atmosphere called the ionosphere. And these are the wavelengths that interest space and plasma physicists the most. So people like Scott Bounds, the club president who works on space physics research, likes to study radiation at these very long wavelengths, and so he uses very simple long antennas. Well, they're actually quite complicated, but they look simple. Long antennas, and he flies them in space because if he were to have them on the ground, they would not get the cosmic radiation that they're interested in studying. we're not going to be talking about that type of radio astronomy tonight. We're mainly going to focus on the part that you can easily see from the ground, and we're going to talk about telescopes that are pushing the frontier of trying to detect the shortest types of radio light. The challenge there is that the water vapor in our Earth's atmosphere, okay, we've got quite a bit going on tonight here. Even though it's not raining, the atmosphere still carries, it's very humid outside. It means that there's a lot of water vapor sort of activated in our atmosphere. And that is problematic for these shortest radio frequencies. And we'll come back to this, but the solution is to go to very high, dry places on Earth. And then you can actually find some windows at very specific sites on Earth where you can almost get full transparency. So this is kind of one of the frontiers of radio astronomy, is trying to push into this wall with better and better telescopes. So that's what we're going to be talking about a little bit later tonight. Now, in terms of the radio sky, this is sort of a picture of what it would look like if you guys had radio eyes, okay? So the radio sky is actually quite complicated. There's a lot of stuff that emits radio waves, and of course we just can't see it, and so sometimes it's hard to come to terms with or grasp. But I'm going to take you through a tour of some of the really fantastic objects like distant galaxies, nearby galaxies, and even explosions of dead stars in our own galaxy that emit radio waves. So these are not things that you can see with your eye, but we can reconstruct images using radio telescopes. Now, I'm just going to very quickly go through some of the processes, some of the physical processes in the universe that create radio waves. Okay, so as opposed to optical light. So one of the first things that creates radio waves is something called synchrotron radiation, which is simply charged particles, plasmas, groups of electrons, groups of protons, moving around a magnetic field, getting sort of trapped by a magnetic field, and as the charged particle spirals around the magnetic field, it will emit a radio signal. Okay, so a lot of what we observe in radio astronomy, as opposed to stars that you see in optical astronomy, is material that's magnetized. So a lot of radio astronomers study the magnetized material in our universe. And from these observations, you can learn really neat things. You can learn how strong magnetic fields are in the universe. You can learn how much energy these particles carry. And when I'm talking about charged particles, I'm just talking about usually it's hydrogen that has been heated by something. Hydrogen is a proton and an electron. Both are charged. When they're heated high enough, they separate, and then you get a plasma. That material then, if there's a magnetic field around, will be attracted to the magnetic field and radiate radio emissions. I'm not talking about obscure material. This is the stuff of which we're all made of, okay? But under certain extreme conditions, you can get synchrotron radiation. So these are often exciting things. These are gases falling into a black hole, an exploded star, jets of emission coming off the surface of the sun. These are the types of things that are magnetized in our universe. You can also learn some really interesting things about which way the magnetic field is oriented. Another thing you can learn from radio astronomy is thermal emission. This is just gas that's glowing, okay? So this doesn't involve a magnetic field. This would just be a beautiful nebula around a star cluster that's just been heated by the stars, and you get radio emission from that process. So here's an example of what an optical image looks like of a nebula, and here's an example of what the radio nebula looks like of the same object, okay? You can often compare what you see in the radio to the optical and learn valuable things about the object. So what can we learn? You can learn in the radio, you can get a very good handle on how much mass is there. So you want to know how many stars was this nebula capable of making before it made the cluster of stars that then it blew out a hole in. Or you want to know if this nebula is going to make more stars, how much could it make? All right. You can also learn about the density of particles in this nebula, and you can also figure out, you can compare how much starlight these stars are giving off with how much starlight is necessary to keep this nebula glowing. Okay, so those are the kinds of things we can learn from radio measurements. And the neat thing is, I just told you about two main mechanisms in radio astronomy. One's magnetized, one's not. They have different signatures in the sky, okay? So the magnetized signature, as you study it at different radio wavelengths or frequencies, it gets weaker. So if you observe the same nebula and you see that as you go to higher and higher frequencies, it drops off, then you know that you've got a magnetized source. If you see that it pretty much stays the same, then you know that it's a thermal source. Okay, and so this is a very important thing that we use in radio astronomy, where we can actually pull out some physics from making measurements of the same object, like the same nebula, at a number of different wavelengths. And you do this, optical astronomers do this too, they call it. For those of you in the audience who are optical astronomers, you do things like you look at the ratio of two colors of a star. That can tell you something about its temperature. Here you look at the ratio of two wavelengths of observing, and that can tell you something about the physics in the object. So it's just a radio astronomer's way of doing something that we do in optical astronomy. Now, one of the neatest aspects of radio astronomy is the plethora of spectral lines. So in optical astronomy, we've got H-alpha, we've got tons and tons of spectral lines. We've also got them in the radio. We've got a lot of them. Okay, we've got atomic hydrogen, which is probably the most abundant component in the entire universe. So we get that transition at 21 centimeters, which has a wavelength of about this long. Okay, and that's everywhere. You point a small radio telescope out into the sky, even from Van Allen Hall, or even on a cloudy night, you will see the universe light up in atomic hydrogen. Okay, we have radio recombination lines of hydrogen. These are outer transitions of ionized gas. And then probably one of the biggest areas of exploration in radio astronomy is molecular lines. So we know the universe is made up of a lot of molecules. We're just finding out how many there are. We are just scratching the surface. And when molecules vibrate and rotate, they give off radio signals. And so we can really study the universe of molecules by using radio telescopes. And the neat thing is, molecules tend to live in clouds of hydrogen that are very, very cold. Now, does anyone know why cold clouds of hydrogen are interesting? We all know why hot stuff is interesting. Well, why would you find a cold cloud of hydrogen interesting? Well, cold doesn't necessarily mean old. So it's true, there's a lot of cold places in the universe are very, very old. We'll come back to that. But that's not the reason it's so interesting. Why would a cold cloud be interesting? It doesn't sound very interesting. Well, you've got dense, cold pockets in a cloud. What could those make? They could make new stars. So even though stars get very, very hot, they come out of little clumps in clouds where the density and the cold conditions, the fact that the gas isn't moving very quickly, that density overcomes the pressure of movement, and those things start to collapse. And if they collapse, quickly enough, and they collapse into a dense enough object, that can form a star, which will quickly get very hot. But the reason why cold stuff and molecules are interesting is that tells us where stars come from. Okay? We also think molecules are interesting in the universe because we know that we're made of a lot of molecules. Okay? And so we wanted to find out how many are out there in the universe. So what can we learn from all these spectral lines? We can learn about the physical conditions of gas, and we can learn a lot about, spectral lines give you a lot of information on movement of stuff using the Doppler technique. Okay, so big differences between optical and radio observing, okay? First one is optical, as we all know, you detect the optical light through using either your eye or the telescope optics in an eyepiece. Or if you're kind of sophisticated, you might have a regular photographic film camera, or these days a CCD on the base of your telescope. And that's how you make the detection. Radio astronomy is a little bit different. The radio wave, the signal from space, is so weak that a major part of its detection is amplifying it. so that you can essentially record it. And so radio astronomy actually arose out of engineers right after World War II who were really busy developing radar systems for the war. And so that whole radio astronomy essentially is a field that's only 50 or 60 years old, and radio detection relies heavily on electronics and engineering. So radio dishes work the very same way. They're usually parabolic, and they have a focus point. And the difference, though, is that the signal, so here's a little diagram, this is a student radio telescope diagram, it doesn't have too many bells and whistles, but you have, or you can have a very simple antenna, but you actually have to amplify it, and you often have to convert the frequency to something that will work in your electronics, and you send it through more amplification, and then you often filter it, and then you essentially reconstruct the wave that you detected cosmically. So it's quite a different process, and for people that like to tinker, it's really, really fun, okay? So here's just another picture. There's your distant radio source. You have incoming radio waves, depending on the curve of the dish, just like an optical, often like an optical telescope. Then, well, in this case, most optical telescopes are flat, but anyway, so this is actually shaped like a parabola, and then there's a subreflector, so it gets sent up once to the subreflector, and that's so that you don't have to house all of your equipment up here that could block some of the radiation coming in. So you have a subreflector, and the subreflector can be very fancy because you might have quite a collection of instruments here to record different frequencies of radio light in different interesting ways. And so your subreflector can actually be quite sophisticated, and you can have many, many, many different feeds down here in the base of the antenna. And so the light ultimately goes down here, and then usually there's a lot of conversion and mixing done at the base of the telescope. Again, a lot of really interesting electronics. And then usually through optical fibers, the signal is transferred underground to some other site where it is received and then recorded and displayed, all right? And in particular, if you have groups of radio telescopes, you will definitely do things underground. If you just have a single radio telescope, it kind of depends on the architecture. All right. So again, I'm not going to read this too much text, but there's a wide variety of wavelengths to observe. There's the high frequency ones that we're going to talk about tonight, the centimeter ones, and then the very low frequency, and then the kind that we observe from space. And because there's such a wide variety of wavelengths, there's also a wide variety of instruments. So here's just some pictures of telescopes, radio telescopes that observe at very high frequencies. So these are millimeter telescopes, and you can see they're all over the world. Then we have, these are examples of telescopes that primarily observe in the centimeter range. Okay, so millimeter is very, very, very short wave. Centimeter is more something that you can measure with your fingers, and these are examples of telescopes that observe in the centimeter. And then low frequency waves are usually longer than a meter. Okay, and the neat thing about low frequency waves is that you don't necessarily need a smooth collecting dish to collect something that long. This is where you start to get into the realm of wires and very simple kinds of dipoles, where you don't actually need the surface area to be smooth. You can see these instruments that operate at these very, very short wavelengths. You have to have a very smooth surface, not as smooth as an optical telescope, but it does have to be smooth nonetheless. And so some of the cost and the engineering required for these telescopes make it less likely to have many of them. Whereas down here, you can actually, at these lower frequencies, if you can build a prototype, oftentimes for not that much cost, you can multiply it by hundreds of thousands, and you can fill in. In the case of LOFAR, which we'll look at later, you can actually fill in many, many, many tens of thousands of dipoles very quickly for not that much cost. So I'll just take you on a little tour of some of the radio telescopes you may have seen. These are big single-dish telescopes. Again, here's an antenna in Australia where the inside part of it is relatively smooth and consistent. That's used for slightly higher frequency work. Out here, it's more just a wire backing, and you can use the entire collecting area for the longest wavelengths. And so as a way, it would be more costly to have built out this material all the way to the edge, so they decided based on their science needs that they didn't need to do that all the way out. Many of you are familiar with Arecibo, which is a very large radio telescope in Puerto Rico. It's soon to be superseded by a telescope they're building into a valley in China called the FAST telescope, which is about the same size. Both of these telescopes, the one in Puerto Rico and the one in China, are actually telescopes that are built into the natural topography of the land. So these are places where there's a deep sort of parabolic shape, and they didn't have to disturb too much of the land to put the telescope in. Here's an example of a telescope on a high mountain in Spain. This is a 30-meter, very, very high-frequency radio telescope. And here is a picture of the 100-meter across radio telescope in West Virginia. This is one of the most powerful telescopes currently in the world, and it's luckily located in radio-free, quiet zone in Virginia where there's no cell phones, there's no transmission of radio waves, so it's relatively radio quiet. Now, you might ask, this is 100 meters, 300 meters, is about the largest size that we can build a radio telescope. Why do you think, but you all know, you've seen images of many radio telescopes spread out over a field or out in the desert. Why do you think we would do that when we could just build a telescope like this? What do we gain by having the telescope spread out over an even larger area? Diameter, what does diameter give you? It gives you resolution. So you can make sharper and sharper images. And the comparison I like to make, and this is not meant to be a math lesson here, but I just want to show you that the way we figure out sharpness or resolution is we take the wavelength that you observe at and you divide it by the diameter of the dish. Okay? So here we're going to observe at 20 centimeters, and our dish is 64 meters across. So our resolution is going to be 0.2 degrees, which for any astronomers in the audience is pretty coarse, okay? It's not that sharp. The pictures you see from Hubble are not 0.2 degrees. The pictures you see from Hubble are closer to 0.1 arc second, okay, which is a very small fraction of a degree. So you couldn't get a Hubble-like picture from this type of telescope, okay? So here's the comparison. An optical telescope that's 10 meters, which is pretty big across as this room. You have a wavelength of 500 nanometers, which is very, very small. That resolution is going to be 1/100th of an arc second. So a couple of orders of magnitude better than this radio telescope, even though this radio telescope is bigger. So the reason is because the wavelength is longer, you have to make a much bigger telescope. And so we go to interferometry. And so we spread our telescopes out then over many, many kilometers. And by doing that, we can get fraction of an arc second resolution and make pictures as sharp as Hubble or the best ground-based telescopes. So that's why we do interferometers, and so most radio telescopes now have moved toward interferometry, and I just thought these are some of my students a few years ago out at the VLA. This is a telescope I use routinely for my research, and I didn't ask her to wear this Hawkeye t-shirt, but she did, and so that was a good thing. These are students who probably graduated 3 or 4 years ago now. Ray Lynn went to become an aeronautical engineer for NASA, and Kelsey is finding exoplanets in our galaxy, and she's getting her PhD at Berkeley. Here's a picture of me in front of the VLA. You can see there's a lot of wildlife out there. We often see antelope and cows. It's a big plane, and the National Radio Observatory rents these little spaces so that they can spread these telescopes out, and they rent them from farmers. So that they can spread these telescopes out across the desert and simulate a really, really big telescope. This is actually what you do. You don't actually get to be outside very much. So here they are sitting at a computer console late at night working. And here's a picture of me. This is from many years ago now, observing, being actually in control of the Owens Valley Array in California, a smaller array of telescopes I used in my dissertation work. Here's the Australia Compact Array. So the beauty of having telescopes across the world is, as you guys know from knowing a little bit about astronomy, you can see different objects from different parts of the world. So in Australia, you get a stunning vista of the southern Milky Way, where a lot of action is happening. And you get the Magellanic Clouds are right overhead, and so it's very, very beneficial and actually complementary to have these telescopes in different parts of the world. Now, we have one in our own backyard. Some of you have seen this one on the Coralville, near the Coralville Reservoir on Lake McBride. This is there's a real-time webcam on the National Radio Astronomy Observatory website. And so the telescope looks like this when it's kind of pointed upwards. And this telescope is really neat because it is part of the world's largest radio telescope right in our backyard in North Liberty. It's not associated with the university. In fact, I've tried and failed to get time on this telescope before. So in order to use this telescope, you have to write a proposal to the National Radio Astronomy Observatory. They review it and tell you yay or nay. And then if you don't go to the site, you do it all over computers. It's part of a network of 10 telescopes that are spread across across our continent. So the longest baseline, or the longest diameter, which will help you with resolution, stretches between Hawaii and St. Croix in the Virgin Islands. All right? Now, the weather is not that great in those places for astronomy, so observing at the shorter wavelengths is a little tricky. But for long wavelength observing, it's great. You just have to have an object, though. It's quite complicated with the timing. So these telescopes will observe the object first, and they'll timestamp the data. These will observe them later, and they will be collected and correlated later in real time. We like to go out to the North Liberty antenna a lot, so here's pictures of Professor Spangler and me with some students a number of years ago taking a tour. One of these years we want to get the club members and another public out there, because there's two operators that work full-time there, and they get a little bit lonely and like to meet real people and like to also talk to astronomers. So this telescope observes as part of the VLA every day, 24 hours a day. So they have data recording. Now they use discs. They used to use magnetic tape, and so they can record for very long stretches of time with nobody there. And then the technicians go and check the data. And everything is controlled from New Mexico. The headquarters of the VLA is also the headquarters of this array. But this makes some of the most stunning images in astronomy. So let me just take you now, in the next few minutes, I just want to take you through some highlights. Some of these are more recent than others, but some highlights as to what we can do with radio astronomy. And I want to spend the last few minutes talking about these new big projects. So one of the main things, as I said, we do in radio astronomy is we study molecules. And we study how and why stars form, because this is a process that you can't see optically. So remember we said that these interesting molecules were in places where the gas was really cold and dense. Well, guess what? When you've got really cold material and really dense, optical light cannot get out. Okay, so these are places in your Hubble images or images that you see in optical that are dark. So has anyone ever looked at a picture of a star-forming region or even the Milky Way and you see those dark bands in it? You're tempted to think that that's a place where you're looking deeper in the space, a hole. But actually what you're seeing is like a black curtain. So you're being blocked from seeing what's behind it. Well, radio astronomy gives you a chance to penetrate through that darkness. And so this is a fantastic picture of a star. You can't see the star because it's invisible, but you can see the gas that it's affecting. And as the star is made, even though the cloud was cold and dense and kind of boring, that star brings a lot of energy to the system, and it spins and it rotates, and there's a disk of material whipping around that needs to release energy, and it releases energy in the form of these jets. But again, you can't usually see them optically, so you see them in gas. And the red and the blue tells us that they're traveling at high speeds in different directions. So again, radio astronomy gives you a window into something that you can't see optically. Now I hesitated, this is a very technical image, but I just wanted to show you that we are only at the beginning of understanding these molecules. So all I'm showing you here is a clump of gas that's going to become a star. And again, you could never see this optically. Every single thing you see here, all of these chemical formulas, are different molecules that have been detected, okay? And these were detected with the sub-millimeter array, okay? This is a current telescope, all right? Keep that in mind later because we're going to come back to these molecules. these are just the profiles of what the molecules look like. So again, we can understand the molecules exist in these cold clumps that form stars. These are also the molecules. Many of these are the molecules of light. You'll see that many of them involve carbon, hydrogen. These are the kinds of things that we're very familiar with here on Earth. These are the kinds of molecules that can form the basic building blocks of life. Radio astronomy can also tell you about how stars heat gas. So here's a picture of a star cluster, and here's a picture of a cloud of gas that's been completely heated and kind of a little bit annihilated by this star cluster. This is in the region of the galaxy that I study. And you can see here the colors represent, again, velocity flows. So radio astronomy can tell you a lot about motions of gas. The other thing that you may not realize is that stars, even our sun, give off radio waves. So everyday stars give off some level of radio waves. The sun doesn't give off too many, but more massive stars, the kind that live dramatic lives and become supernova, on their way to becoming supernova, they give us signals that they might be about to die. One of those signals is they have a wind, a powerful wind of material, like the solar wind, but much more dramatic. And so here are images of stars that are losing material off of their surfaces through wind. So you can see the mass loss rate here is 8 orders of magnitude greater than what our sun puts out into the solar system. Okay? Imagine that, Scott, for your work. Scott studied the interaction of particles from the sun as they make their way through the solar system. And they are much less dramatic than with these very massive stars. We can see these things in radio emission that you can't see in optical. Another thing you can see in radio emission are the remnants of dead stars, okay? And so here's a supernova. This is a star that has exploded. Again, you don't see the signature as often in the optical as you do in the radio. And the radio emission can give you a lot of insight into the explosion energy and the explosion speed as it propagates into the material. Here's an example of a supernova that actually has left behind the corpse, and the corpse is moving. It has some relative velocity to the side, which is very interesting. And so again, we're able to see this in radio. You couldn't see this in the optical part of the spectrum. The region of the galaxy that I study, here's an example of where you have a lot of dust and cold material blocking your view of the bright stuff. The region of the galaxy I study is completely obscured from your eyes. So those of you who know a little bit about astronomy in the audience will appreciate this. The center of the galaxy is behind 30 visual magnitudes of extinction. Okay, so it's not possible at all to observe any radiation in the optical part of the spectrum from this region. However, if you turn your radio telescope toward this region, you see brilliant images of radio emission. This is one of the brightest regions in our galaxy in radio light. And so I'll just show you some pictures of what the radio images show. Radio images have helped to discover that at the very core of our galaxy lies a supermassive black hole that you cannot see optically, but you can see material on its last trajectory inwards toward the center of the galaxy. And here's a beautiful image made at a very short wavelength of material that is in the general flow toward the supermassive black hole, which is down in here. And this material actually moves on a cycle that you can measure because of its proximity to the black hole. And so we can trace that year after year and get a measurement of how much mass the black hole contains. There's also very strong magnetic fields in the galactic center. This is one of the areas of my research. And in radio, this is, again, all radio light. You get very detailed pictures. Even you can get vectors that show the direction of the magnetic field in these incredible strands that we are only just beginning to understand. You can also measure in radio, you can see flows of material between galaxies. This image didn't come out that well, but this is a fairly recent image made by that big Green Bank telescope. You can see a flow of hydrogen gas between two of our neighbors. M31 and M33. And so at one point in the past, these galaxies may well have been interacting with each other. Radio astronomy also allows you to sample cold gas that is likely to be associated with dark matter in the outer parts of many spiral galaxies. So these are a collection of galaxies that observers, many optical, many amateur observers, enjoy observing on clear nights. The radio picture tells a very different story. The radio picture shows that these galaxies actually extend almost twice, in some cases, out beyond the optical edge. And this region is filled with cold atomic gas that is presumably mixed in with some of the dark matter that keeps the motions in these galaxies going strong even at their edges. And so this is, again, another place where radio astronomy can show you a signature that you can't see in the optical. One of the last examples of radio astronomy is in galaxies that appear to be very quiet, but actually have monster black holes at their centers. And in the optical, you don't see so much, although in this particular galaxy, M87, which some of you are familiar with, you can actually see a narrow jet coming out of the center. In radio, this is what the image looks like. And this is, that entire picture behind it would only fit within my laser pointer here. So this is a flow of material out from the energetic region near the black hole that is pushing charged particles way out beyond the galaxy's rim. And here's another, this is a brand new image from the Very Large Array, showing again how powerful these jets of material coming out of galaxies that have a supermassive black hole are, and how complementary these two pictures are, right? You never would have guessed necessarily, just looking at the optical telescope, that there was so much energy being created in this system. All right, so let me focus now just for a few minutes on the very highest frequency. So this is one of the new international projects that we have developed in radio astronomy. It's very exciting. We said before that water vapor, heavy in the atmosphere, is a problem with observing at the very shortest radio wavelength. So to solve that, you need to go to high elevations, you need to go to places that are very, very dry. So high deserts are the best pick. So possibly the highest, driest site on Earth is at an elevation of 16,400 feet. It's in the northern Chilean desert, and it is the site now of a 60-element interferometer that is a major international project. And this is a cartoon. I have some real pictures in the next few slides, but this is a cartoon of the array design. And so they have these telescopes, and they're movable because you want to change up their positions. Very complicated engineering. Up here you have to have oxygenated small cars that can drive they can lift the telescopes, because at that altitude your brain doesn't function 100%, and so they have it all engineered, and this instrument is now offering us a 1 to 2 order magnitude improvement in observing at this wavelength regime. The sun never sets on Alma, is what they like to say, and that's because there are collaborators in North America, South America, Europe, and Japan. And one of the reasons why is that this project probably cost $1 to $2 billion in its entirety. U.S. is making a third. We are providing a third of that support for the construction and operations phase of the Alma telescope. And so this is a very, very exciting, but a very significant project. I'm just going to breeze through these slides, but here's Chile. So we're in the northern part of Chile, and if we zoom in, you can see here's Santiago, if you're all familiar with that, and here's Antofagasta, and Alma is located to the east of Antofagasta. And if you zoom in further, you can see this is a very high salt plain. It has not officially rained here in hundreds and hundreds of years. It is so dry, and it's a very popular area for tourists to visit for the salt and for the very extreme wildlife that lives at these elevations. This is the contractors' camp. There were 500 contractors working to build the array when it was built in the last 2 or 3 years. There are all sorts of things that happen there. Here's the volcano exploding, a view from the contractors' camp. This is so basically when you run a major array like this, you don't have astronomers, you barely have anybody up at the high site during operations. There was a lot of people up there during construction. We want to keep as many people lower down as you can. So this is the array operations site, the technical building. This is at the elevation of 16,570 feet. Here are pictures of the antennas being constructed. So they were driven up to the high site, or they were driven up to the, there's also a lower site. I thought I had a picture of it. There's a lower site. So some of the construction was done at the lower site where people could think clearly. And then the telescopes were delivered to the high site. So I'll just show you again, these, for any of you in the audience who are young and still thinking about what you're doing, these major telescope projects have so many opportunities for people to join in, no matter what their expertise is. So you can see a telescope like this requires unbelievable engineering in the paneling, in constructing, in the building of these things, and the back ends that actually convert the signals to images are just stunning in their engineering complexity. And so many, many, many hundreds of people all across the world contributed to make this project a success. So these are 3 example receivers from different parts of the spectrum that they sample, okay? And so they all go on the back end of every single one of the 60 telescopes. So each one of these things had to be created 60 times over. And you need to make some spares, okay? This is what they look like when they go into the back of the telescope box at the bottom, in the antenna. You have the subreflector up there, it points the light down, and then you have the antenna, we call it the antenna room sometimes, and that has all the back ends, we call them, the place where the light is converted and filtered. And this is what the back end room often looks like coming off the back of the telescope. To move these things around, you need an unbelievable transporter. So this is a picture, I think this is a transporter being constructed in England. And then this is a cartoon. I didn't have time to actually get there. And obviously, the transporter has been used. There's 2 of them. They're used almost every day for various things. But this is a sketch from the early days of what the telescope would look like. This is the size of a person, okay, so you can see the relative size. This is a stunning image. Here there is snow. Of course, after they built the telescope, they had more precipitation than they did in half a millennium. And so they've been a little rough going with the actual observations, but luckily the back ends that they built first were the longer wavelength ones. They wanted to get things up and running. So this is a picture. This is a stunning picture from just I think 2 months ago or something. The Alma Array is now complete. It has been operational for the last year or 2 in shared risk mode, meaning you could use even 20 of the Alma telescopes is an order of magnitude better than what we can do right now. And so I have put in countless proposals. I've probably put in 10 proposals so far. They've all been rejected. And so I'm trying to make my way into the field. It's incredibly competitive. For the first cycle 0, they got 800 or 900 proposals, and they chose about 25. And for the most recent round, they had 15 or 1,600 proposals, and I think they chose several hundred. So it's really, really competitive to break into the field and to actually get time. And then even if you get time, a lot of things go wrong because it's not officially all turned on yet. So we're waiting desperately for the cycle 2 proposal call, which will be in full operations mode. Unfortunately, 2 or 3 days ago, some of the workers went on strike at the site, and so there's all sorts of political problems now. So anyway, but this is another image. This is a real image of what the telescope, what each antenna looks like. And again, you can see that at these high frequencies, the surface is very, very smooth, and the antennas actually don't have to be that big, because you remember, wavelength over diameter, the wavelength is very, very small. You don't need as big a telescope. But these are 10 and 12 meter antennas. The U.S. built a third of them. Italy built a third of them, and Japan built a third of them. So that's how we divided up the work, and somehow all the telescopes operate smoothly together. It's really been a major, major international partnership. And so here's this is a real image of the Milky Way, which you can see beautifully over Alma for 12 hours a night. Here you only get a couple hours if we're lucky of the Milky Way. And I thought I would just show a few of the results from Alma's first year or so on. This is, Alma was able to catch a solar system in the process of forming. So this is a star, Fomalhaut. It's only 25 light years away, so we're relatively close by. And this is a Hubble Space Telescope image showing that there's a disk of material that's still settling into its formation. And in that process, they actually found a planet that moved from year to year. So not only do you see the material settling in to make planets, but you actually see a planet moving in that disk right in here. Alma is able to trace very hot dust that is associated with how planets form. And so this is Alma's picture of the dust continuum, and so you can see we are matching the resolution almost to Hubble, and for the first time at these frequencies we're able to do that. And so I don't think I have the montage in my presentation, but a few months ago they released a beautiful montage of an updated Alma image with an updated Hubble image, and they just were laying right on top of each other. And scientists are then able to pull out information from both telescopes. This is an optical picture of the antenna galaxy. And this is one of the results from Alma. For the first time, we're able to study molecules that are going to make new stars right at the intersection point between these two galaxies. And so again, something that complements what you know in the optical can be added by radio telescopes, and in particular, this new Alma instrument. Alma has discovered that in the distant universe, galaxies were more massive and more actively making stars than we thought. And one of the ways that you do this is by looking deep into space, into galaxy clusters, and seeing lensed systems. So these are very distant galaxies whose light passes through a gravitational lens. The galaxy emits a lot of radio waves because it's making a lot of new stars. You otherwise couldn't see it. And so we're essentially probing very, very distant galaxies that are much heavier and more active than we thought they were. So it gives us a window into what's happening in the very early universe in a way that light that kind of runs out of juice can't tell us. Now I'm just going to mention two other projects here, and then I want to end and take questions. The LOFAR is a low-frequency project, and as I said earlier in my presentation, the beauty of low-frequency astronomy, radio astronomy, is you can build a relatively simple antenna and duplicate it many times over. And so LOFAR is an array that's completely dedicated to observing below 250 megahertz. So this is approaching the lower end of what we can do. And the reason why this is very interesting is the material that was bright when the universe formed has progressively gotten older and colder. Somebody said that cold means old, remember that? This is where it's at. So if you're interested in light that's really, really old, it gets very, very much redshifted. So radio light that you're interested in from, say, the hydrogen atomic atom will get shifted to very low frequency. So if you want to study the earliest hydrogen in the universe, you want to use LOFAR. And so LOFAR is being built up. It's a telescope that's already been turned on. It's already making some exciting discoveries, but it's based all over Europe, and it is perched to make some of the first observations of the earliest hydrogen in the universe. So just to reiterate that point, if we think about where we are now, and we think about cosmic time, this is when the universe is in a much hotter and denser state, and hydrogen atoms first were stable enough to give off radiation. That was a long time ago. If we want to observe those hydrogen atoms, we need to use radio wavelengths that have been shifted and very low frequency telescopes. We also are very interested in the magnetic field of things in the universe, and that can also be studied at lower frequencies. And so the LOFAR can do both of those things, and it's very actively trying to do that. And it can do it in a way that it's hard to see how this will give you a picture of cosmic magnetism or early hydrogen, but it does. You combine signals from these antennas, these major computing efforts. Again, for those of you who are still thinking about what you might want to do, if you have any interest in computing, this kind of project cannot be worked on without major computing resources to be able to write algorithms that can combine and process data from all of these things real-time on the sky as you're observing. It's really a really neat and exciting field to go into, even if you don't have a lot of interest in astronomy. So putting all this together, the big project on the horizon in radio astronomy that the world is getting behind is called the Square Kilometer Array. This is a project that is at least a decade out in terms of really happening, but the idea here is to create a collecting area that is 1 million square meters, or 1 square kilometer. So you have enough dishes to make the most sensitive, sharpest image radio telescope that has ever existed. To achieve this, the Square Kilometer Array will use 3,000 dish antennas, each about 15 meters, okay, 3,000 of them, not just 60. And they'll also use 2 other radio wave detectors that are not dishes. They'll be more like dipole setups. The antennas will be arranged in 5 spiral arms, much like our galaxy, and again, a massive amount of computing and theoretical work is gone into calculating exactly what combination and layout of telescopes will give the best image quality. So again, a huge amount of computer resources has gone into this image. And the dishes will extend to distances of at least 3,000 kilometers. So we're talking about these antennas out here, these dishes being the scale of continents across. So there'll be a core somewhere, and then there'll be other elements in other continents, which is very, very exciting. So again, this is going to be a major international partnership. This project is going to be at least $1 to $2 billion. Of course, it will be split between countries. At the moment, we have, the U.S. has kind of put its eggs in the Alma basket, so we, at the moment, are not doing a lot of contributions to the Square Kilometer Array, but that could change, and those of us who work in these wavelengths are actively trying to get involved with the current work. So the 2 main efforts, the prototype efforts, are happening in Western Australia, which is a very remote place, no radio frequency interference, and not a lot of people to mess things up, and also a high, dry desert site. So at this site, which is called the Murchison Radio Observatory, they are in the process of constructing 36 12-meter antenna prototypes that are going to operate at about 20 centimeters. So kind of in that regime that's not super long wavelength, but you don't have to worry about all the stuff you do at the Alma site. The Australian government has just awarded this group with a $6 million project fund to build that first group of telescopes, and several of them have already been built. So this is just a Google Maps view of the 2 or 3 stations, or I guess there's about 5 or 6 stations that already exist, and then they're going to plan to build out from there. So Australia has really decided to put a lot of investment in radio astronomy. It's a very exciting place to be working in radio astronomy right now, as well as complementary these wavelengths to what they're doing with Alma. And the final place that is contributing to the Square Kilometer Array development is South Africa. And so again, this is complementary because it's in the Southern Hemisphere, Australia is in the Southern Hemisphere, so these 2 projects will be complementary to stuff we have in the Northern Hemisphere. The prototype array is going to be called the Meerkat Telescope. It's going to operate at a higher, slightly lower frequency and a slightly higher frequency, and it's going to be built in the Karoo Desert in South Africa. So anyway, these are very exciting projects, and we are sending, and the U.S. is sending engineers to get involved at some level, and the work is very complementary to what we're doing in other wavelengths. So my final slide just goes back to showing all of these radio telescopes, and I showed you a little bit of science. I thought you'd appreciate the actual physical telescopes, so it's fun to see. But I hope you feel the same way I do, that radio astronomy has a very bright, exciting future. And I hope I opened up your eyes a little bit to observing beyond the visible. And I am more than happy to take questions about radio astronomy or anything I talked about tonight. So thanks.
Issues with frequency detection. 250 megahertz range, 1 gigahertz range. There's a lot of other stuff going on there.
Do you mean like we call it radio frequency interference? Is that what you mean?
Yeah.
Yeah. So that's a very good question. So a major part of being a radio astronomer, or if you work in a radio observatory, is understanding that a lot of other people use that part of the spectrum. So a lot of personal computers operate at those frequencies, cell phones operate at those frequencies, and so radio astronomy has some very narrowly protected bands, thanks in part to Herbert Hoover, who helped from West Branch, who helped allocate the frequency allocation into the current federal frequency allocation. So we do have problems. So some of the transitions of particular molecules that we're interested in are very heavily protected, and so you couldn't operate a cell phone where a particular molecule is vibrating. Those are very, very narrow windows, so it doesn't affect a lot of those other communications. What we do in practice is when we observe at the lower frequencies in particular, we have to scan through our data very carefully, and so there are algorithms that have been developed for known lines, and then there's also, in New Mexico especially, there's a lot of military communication that occurs in the X band and near the C band, and so those have to be taken out on a case-by-case basis. So we just train ourselves. You always look at your data set, and the thing you look for are signals that are clearly not cosmic signals because they're 10 orders of magnitude brighter, or they're very apparent in the data. So we can differentiate. We usually just edit them out, and then every once in a while I complete observing revolutions.